All right, so I'm a professor at Northwestern University, so I spent my entire career at Northwestern, but I'm also, let's say, decent, if not fairly successful entrepreneur, right? So, but here I'm representing Northwestern today, right? So this is all part of the Center for Deep Learning. All right, so we established, so I'm the director of the Center for Deep Learning, as well as the director for Master Science in Analytics, and as I said, full professor at Northwestern University. All right, so the center has been established about 2 years ago. So it has been established 2 years ago, roughly, and with the mission of disseminating AI and sort of collaborating with industry partners, sort of established Fortune 500 companies as well as startups. All right, so we have two big projects in the center. So one is called DELOS, which is an MLOps framework for exclusively focused on deep learning, right? So and that's going to be the main focus of today's talk. The other one, which is called RIFID, that's a deep learning system for IoT, right? So I'm not going to talk about that one at all, right? So RIFID has already been open source. DELOS, we are about to open source it, right? So we brought it at a level where we are comfortable open sourcing it, right? So the partners of the center, sort of, they have direct input into the development of the two projects. They have access to the students. They can hire students, and so student talent pipeline. And they also can do what we like to call kind of tailored projects. So that's the very last bullet point there, right? So the tailored projects means projects that are tailored for particular use cases at those companies, right? So they're not necessarily related to the two big overall projects, right? So if you want further information, just email to cdl@northwestern.edu or deeplearning.northwestern.edu. Right, so that's our main website. All right, so just quickly, today's agenda. So I'm going to start with challenges with deep learning and model serving. All right, so the focus of today's talk is going to be mostly on deep learning, right? So not traditional models such as random forest, SVM, etc., but really deep learning models. All right, so then we're going to discuss a little bit about architectures and some algorithmic aspects. Right, so I'm going to keep it at a high level, not going into details. So those who are interested, you can find details at the deep learning website of Northwestern. And then I'm going to tell you a little bit about the actual DELOS project and how it works, etc. Right, so that's the agenda. All right, so let's start with challenges in MLOps pipelines. All right, so these are some of the challenges that we have identified. Sort of, I'm sure sort of you have your own in your own company. But so let me start with drift detection. All right, so you deploy your MLOps, your machine learning model, whether now it's traditional deep learning, it doesn't really matter. So you deploy it, and then there's a drift either sort of in your data, sort of context drift, or you can get a drift in labels because of change in business environment, et cetera, right? So it's very challenging to detect the actual drift and then act on the drift, right? So that's the first challenge. Another challenge that was brought up actually by our industry partners is that labels, ground truth, usually have lags, right? So when you perform inference on your samples, you are not immediately after that getting labels in order, so suppose you want to detect drift by measuring, let's say, accuracy or F1 or whatever is your favorite score, right? So you cannot do that right away because labels sort of will trickle in sometimes in the future, right? So that's always the case, right? So and in applications such as, I don't know, let's say healthcare, where you're making diagnosis on some, predicting, so diagnosis on some diseases, sort of, it might as well take months before labels actually come in, right? And there's, so a few years ago, I don't know, 4 or 5 years ago at the conference, I heard a very nice kind of quote saying that you actually put your best data scientists in MLOps, on MLOps, right? So, or in other words, sort of at that time, actually the term MLOps was not there yet. it was on model serving, right? And so this is one of the reasons, so dealing with drift is one of the reasons why you actually need really top-notch data scientists in the model serving phase. Right, so the second challenge in MLOps pipelines is usually they have no interoperability, right? So they are built as proprietary or for that matter sort of open source software and tied to a particular architecture, particular design, and it's hard to port them, right? So especially these days when you have your on-premise IT resources and you have in the cloud, and maybe you're even using two different cloud vendors. So you want interoperability, and that's usually not there, right? So and model maintenance sort of it's tied with interoperability, right? So model maintenance sort of as versioning, keeping track of versions of the model and potential canary deployments, etc. Right? So this is another challenge, and then sort of model serving, it's a continuous long learning process, right? So you have to continually be detecting drift and potentially retraining your model, right? So in lifelong learning, sort of in machine learning, so there's a common, very known challenge, which is called catastrophic forgetting, right? Because when you retrain your model, you don't want the new model to completely forget about what happened in the past, all right? So and how do you retain this fact that a new model sort of should not forget about the past, right? So, and I'll talk a little bit about this in the second part of the talk, right? And then the last big challenge is risk of actually introducing a new model, right? So a new model now I actually mean after you retrain your model, so you have your model, it's being served, and you retrain it, and then there's always the uncomfortable level of uncomfort because you don't know how your model is actually going to behave, right? And so those are the risks sort of putting a new model in production, right? So now you can argue, or not argue, okay? So if you don't have an MLOps solution for deep learning, you're probably doing it manually, right? So doing it meaning model serving, so you're performing it manually, right? So what are the challenges, right? So first of all, manual stuff, it's always very hard to scale, right? Because you need humans, and we all know that data scientists and machine learning experts are a very costly resource, right? So having sort of army of data scientists for model serving and for various models, etc., it's a very costly premise, right? The second sort of, or another challenge, say, with manual stuff is, so when you train your model for the very first time before you put it in production, right? So now, again, the focus here is on deep learning, right? So it's actually quite common that your model is going to train for several days, right? So and perhaps even weeks, right? But when it comes to model serving, so you detect drift, you can't wait now for a week or you can't wait for a few days to train your new model, right? Because that's just sort of in those 2 days then, between the time when the drift is detected and the time where training is actually going to be finished, so that's 2 days, all right, your model will be making, quote, bogus or very questionable predictions, right? And you don't want that to happen, right? So training times in model serving, or what we actually call retraining of your deep learning models, has to be done much, much quicker, all right? So that's another sort of challenge and a reason why, for example, if you're going to, again, follow the same process training steps as if you're going to follow the same training steps and procedures sort of as the very first training, sort of it's not acceptable because it's going to take too long, all right? And second, if you employ manual process, sort of it's, quote, long time to market, which essentially what I mean by this is you're going to have a brand new use case, and with all the manual labor that's going to be needed to deploy and start model serving, sort of, you cannot scale that to many, many use cases, all right? So it might work sort of if you are kind of small company or SMB and you have perhaps sort of one or two use cases, yeah, then it might work. But if you have many, many more in like a large organization, doing that manually, so it's not going to scale, right? And second, so this is actually something that we just kind of are touching the surface. We haven't done a lot about it, all right? So, but if you have humans sort of, it's well known that humans sort of, we introduce bias and fairness, right? Now, you can clearly argue that models do as well, all right? So that's something that we are currently looking at, all right? So, but bias and fairness is a very hot topic in machine learning lately, all right? But humans sort of are, the point here is if humans are going to be making a lot of decisions while after you deploy your model, sort of, it's likely that you're going to encounter bias and fairness. All right, so here's sort of a framework, sort of a model serving framework, and now I'm going to focus, I mean, it's general one, right? So you have data that comes in that you want to do inference on, so you have inference module, then you have the monitoring and retraining model. So the monitoring model here in this flow chart, sort of it captures the actual drift detection inside, right? So and then the inference samples are then combined with training samples for retraining, right? So you have the retraining module there as well. All right, so the next few slides are sort of a little bit technical, but I'm going to keep it simple, so they're not actually not that technical, right? So first, what do we do in terms of monitoring and retraining, right? So what I'm going to talk now relates exclusively to our model serving solution, focusing on deep learning. All right, so kind of new materials, right? So first of all, you want to detect automatically. So we want to have, or our system has an automatic drift detection system. All right, so based on the fact that your incoming data is sort of structured or unstructured, but you have a deep learning model. All right. So we also consider lag of labels, right? So lag of labels is what I mentioned earlier. So your labels are actually going to come in later, all right? And then we predict the likelihood. So our drift detection model actually predicts the likelihood of drift happening, all right? So it's sort of standard type of, it's actually not standard type of classification, okay? Because you, next slide sort of shows that it's actually an ensemble type of a model, right? And clearly sort of our goal is to reduce false drift detection, all right? So here's the main idea, sort of, I said that we have three models, actually, let me put everything here. We have three models, all right? So the first one is based on performance metrics, all right? So such as F1 or accuracy, all right? So we have a time series, so we monitor let's just focus on accuracy, right? So we model accuracy in time, so that creates a time series, and then we make, quote, a prediction for the next value in the time series, right? So and if that prediction is, quote, off, then it's a candidate for being a drift, right? So this time, right? So I'm referring to time, right? So then that time is a candidate for being drift. All right, so, and this module requires labels, all right? So we compute accuracy, clearly we can compute accuracy only for samples that already have labels, all right? So which means that some of the samples sort of are gonna be stale, all right? So, but nevertheless, sort of, that's, it's something you have to deal with, right? So there are no other ways to cope with that, all right? So the other two modules actually don't require labels, all right? So they're kind of, quote, unsupervised, or in other words, so they deal mostly with data drift, right? So model uncertainty is one, all right? So we somehow calculate, I'm not going to go into details, all right? So we have a routine that calculates model uncertainty, and it's not just simple maximum probability, right? So if maximum probability is high, sort of then there's high model uncertainty, all right? So it's known that just looking at maximum probability when you make classification tasks, sort of, it's not a good measure of model uncertainty, all right? So we have our own routine for model uncertainty. We monitor it in time. We try to predict what's going to be the next value, and then if it's out of whack, sort of, that's another flag for drift, right? So the third one is the Hellingen distance, which is essentially a relatively simple measure for the difference or distance between two data sets. All right, so the two data sets are the old data set and the most recent data set that you used for inference. All right, so you compare the two, and if that value is large, sort of that's an indicator for drift. All right, so each model flags whether it's drift or not, and then we use Ensemble to come up with a final recommendation whether it's a drift or not. All right, so in the final recommendation, sort of, it's assigned a little bit more weight to the classification error than to the other two. Right, so you see the formula on the slide. All right, so next, let me focus on model retraining. All right, so these are the only Greek equations that I have here, and you don't need to pay attention to that. I said the major challenge here is computational time, and second, catastrophic forgetting. Right, so because you are retraining your model many times, sort of along the time dimension. Right, so as samples come in model serving. Right, so we use the ideas of EWC, elastic weight consolidation. All right, so in other words, we impose that the new weights should not be that far from the old weights. All right, so and now each weight sort of gets it's not really a hyperparameter. Right? So it has a parameter as to how much should you deviate from the previous weights. All right, so machine learning theory says that that's related to the Fisher matrix. Fisher matrix is very hard to compute. All right, so in essence, we approximate the Fisher matrix by the gradients of the neuron activities. Right, so that's kind of the formula there. Right, so that's how we cope with catastrophic forgetting, and how we cope with. Next slide. Yes, how we cope with the fact that you want to have very fast retraining. Right, so we actually don't do full epoch type training, but we employ multi-arm bandit type ideas. Right, so which essentially you take your mini batches and use multi-arm bandit in order to assess sort of which mini batch produces or is likely to produce lower or higher. Sorry. Okay, so higher decrease in your loss function value. All right, so that's then drastically, it has two benefits. Right? So number one, it drastically reduces training time, and number two, it actually lets you select samples that you want to use for retraining, right? Because so one other aspect that I didn't mention when it comes to retraining is what samples should you use, right? So if your model is being served, say, for 1 year, right? So and it needs to be retrained now because of a drift, do you really want to use the entire 1 year of samples? Maybe yes, maybe not, right? So because those old samples, so they might be completely irrelevant, right? So you need to, so there's a different challenge also hidden inside drift detection, which is which samples should you actually use for your model retraining, right? So the MAB approach actually allows us to also select what samples on the fly, kind of what samples to use for retraining. All right, so as I said, I'm not going into technical details, so that's all on the kind of technical side, all right? So our system is actually Kubernetes based, right? So it actually has been developed from day one on top of Kubernetes. So it's Kubernetes native, actually MLOps framework, right? So what this allows us is definitely interoperability, right? So it can easily run on Google Cloud Platform or AWS or Azure or your on-premise Kubernetes cluster, right? So you don't need to do anything really. It's just we actually use CI/CD as well, all right? So we use Argo CD, sort of it deploys sort of in a matter of essentially just one click through Helm charts, all right? All right, so it has then, because it's based on Kubernetes, sort of it has by default sort of availability that kind of inherited from your Kubernetes cluster, right? So and I assume sort of Kubernetes clusters are not going to go down just like that because they have several nodes, etc. Right? So it has increased availability, right? Interoperability, which is something I already mentioned, right? So it's easy to port our system from one Kubernetes cluster or not, to another one, in other words, from one cloud provider to another one, or even leveraging several cloud providers at the same time, right? And then scalability, that's the usual advantage of Kubernetes, right? So you just add new nodes and you increase your replica factor in the deployment, and you have scalability, right? So very easy way to achieve scalability, right? All right, so All right, so motivations. Why did we decide to develop Delos? Okay, so Delos is the name of our platform, right? So first of all, an easy-to-use, interoperable, and scalable platform, and that would sort of hopefully improve the ROI of deep learning AI-based models. All right, so those were the two driving factors. Why did we develop the Delos system, right? So some more kind of specs around the design of the actual system, right? So efficiently retrains your model, and it has drift detection and monitors as well, right? So we have Grafana, you will see that. We have a Grafana dashboard where you can see your performance metrics, you can see your drift in time, your predictions in time, etc. Right? So it allows monitoring, and Kubernetes native. All right, so I already said that. It handles structured and unstructured data, even though the current version handles only structured data. Right? So, but we are building currently support for unstructured data. And we ensure model validity because one can do canary deployment, sort of you can specify how much, what proportion of traffic you want to go to the beta version versus your current alpha version, for example. You can configure that through config maps, or it's going to be automatically then readjusted. All right, so then we also provide, all right, so because it's on Kubernetes sort of scalability and extensibility, we have APIs, for example, when labels come in from the samples that have already been served, so we offer an API for that. We have enhanced security. Enhanced security is through Istio, right? So we have on the front end, so there's Istio, and also for all of the services inside the actual system, so they run on top of Istio, so there's enhanced security. Model deployment strategy, so that relates to the canary deployments, all right? So we allow canary deployments, and we have dashboards for monitoring, which is also something I already mentioned, all right? So it requires persistent storage because samples, for example, where we do inference, so they're stored somewhere, right? So that's why we require, and labels for that matter, they're stored somewhere. So one has to first have a persistent storage available in the Kubernetes cluster, and then you just specify what is your persistent storage. And it can be anything, all right? So our current tests are based on clusters, but it can be whatever persistent storage you use, right? So you can as well hook it directly to S3 or buckets in the Google Cloud platform, right? And it's customizable. It's easy to customize it to specific use cases, right? So, for example, okay, so one thing that I actually don't have on the slides is entire retraining is based on computational graphs, right? So we don't assume any particular architecture of your deep learning model. All right, so you specify your training model by means of an ONNX file, right? So, and most of the, if not, actually I can even say all of the deep learning frameworks from PyTorch, TensorFlow, et cetera, so they support ONNX, right? So you can export your trained model in ONNX. We read the ONNX file, we create the computational graphs based on that ONNX file, and then our retraining is based exclusively on top of that computational graph, right? So one challenge with that is ONNX actually, it's supposed to be a model for inference, right? So that captures inference facts. So that means making predictions. So ONNX, as of now, does not save or encode your loss function, all right? So in order to retrain, we need the loss function, all right? So you have to specify a particular JSON file that specifies your loss function, all right? So then we combine that JSON file with your with the Onyx and, with the computational graph to come up with a training model. All right, so it's completely portable, right? So that's or not portable, right? So we are not assuming any underlying architecture of your deep learning model, right? So that's the key takeaway here, right? So it's built on top of CI and CD, right? So there's Argo CD where sort of you put your YAML files there in your GitHub repository, and then actually not your, but Delos's, our system's YAML files, and then Argo CD automatically adjust for any changes to those YAML files. All right, so and I already mentioned this earlier, it's not yet open source, but it will be open sourced very soon, right? All right, so we call it Delos. All right, so now what does it take to actually use Delos? All right, so you install it by using Helm chart. So all you have to do really is you have to make sure that you have a persistent volume storage in your Kubernetes cluster. All right, so you specify the traditional values.yaml file for Helm charts, and then you install our system. Right, so that's all it's needed. Right, so just one single click. And it's going to install, all right? So some of the requirements, right, so it requires Kubernetes version larger than 1.20, and that's due to Istio, actually. So Istio has some issues with lower versions of Kubernetes, all right? So persistent storage, I already said that, and it also requires core DNS, all right? So because Mongo that we use for storing labels, sort of it requires core DNS, and some other components that require core DNS being installed, okay? But most of the Kubernetes clusters sort of these days, they offer core DNS, all right? So as a user, right, so this is as a data scientist, all right? So as a data scientist, what you have to provide is the initial trained model, right? So that's in the Onyx format that I already mentioned. You need to provide through config maps in Kubernetes, sort of you need to provide your training hyperparameters, okay? Because the same hyperparameters are going to be used for retraining, right? So like learning grades, for example, mini batch size, etc. All right. Then feature information. So by feature information, I only mean whether a feature is categorical or integer or floats or a floating point number. All right. So your loss function, which I already mentioned, sort of we have a YAML file for specifying the loss function, and then in order to quote say not quote okay. So in order to get started with drift detection, especially Halogen distance. All right, so we have to know, we will compare the first batch that comes in versus your training data, all right? So you don't need to specify or share the entire training data, but some representative sample of training data so that we can calculate the very first Halogen distance, all right? So that's the only reason why we need part of the initial training data, all right? So you just need to mount your file system, or so your persistent storage. So that's kind of the next step. And then you install it, as I said, through just simple Helm chart. Okay, so you have to install the actual Istio through Helm charts, and then our system by means of Helm charts. All right, so or a Helm chart. There's just one. All right, so and there's a typical values file where you can make some customization. All right, so high-level flow diagram. All right, so now this is going to get a little bit complicated. All right, so but hopefully it's not that bad. All right, so we have a client, so which essentially is somebody that does model serving, somebody that wants inference. Sorry, somebody that wants inference. All right, and so the key components here are we have the drift model, we have model retraining, and we have the actual inference engine, and we have then also the client API. So this client API is, for example, for labels, right? So or if a client wants to, number one, so specify labels, or if the client wants previous predictions from some past samples, right? So I don't know for what reason, all right? So but we provide that through the RESTful API, all right? So it's actually RESTful API, all right? So so as I said, you have to provide the initial Onyx model, so we put it in your persistent volume storage, and then all of the serving batches that needs to be done, you also just simply put them in a particular folder in the persistent volume, and then our system will monitors that folder, and whenever there's new data in that folder, that's a new batch to serve, all right? So we don't yet have a RESTful API for actual accepting new samples, all right? So, but that's work in progress, and it's not going to take us that long, because that's based on all the other machineries that we have, sort of, that is an easy enhancement, all right? So currently, in other words, currently you dump your, or not dump, so you copy or move your data that you want to do inference on, you move it to one folder, we monitor that folder, and every time there's a change, sort of, or addition to that folder, that triggers inference, all right? So, and again, the RESTful API is forthcoming, right? So whenever there's a new batch, sort of, we run inference, and then we store the actual predictions into Mongo API, right? Or not Mongo. We store it in Mongo by using our internal, or not, by using Mongo's API, right? So, and sort of the standard CRUD type operations with Mongo, all right? So, and then after inference is done on a new batch, right? So the drift module is triggered, right? So to detect whether there was a drift or not, right? And then the drift code findings, right? So whether there is drift or not, and predictions from that last batch, they are then displayed in the Grafana dashboards, right? So you have your typical Grafana sort of UI with dashboards that we have already created, sort of, and this said dashboards, so I don't have a demo, this is not supposed to be a demo session, right? So you can visualize sort of your F1 metrics, accuracy, drifts, et cetera, all in Grafana, right? So we sort of visualize in time, right? So the user can also provide labels, and then those labels are then, through the Mongo's API, they're then inserted into Mongo, right? Okay, so this is the architecture, all right? So there's some other aspects that are less relevant. All right, so let's go, next one, next slide. All right, so this is simplified architecture, right? So I'm not gonna spend time. This is the same as what was last slide, except sort of in a little bit more compact way. So you have the user, so the user interacts. So user is, again, somebody that wants to do inference on samples, right? Or on batches, mini batches of data, right? So the user interacts with the Grafana dashboard, sort of, or in other words, visualizes, inspects the Grafana dashboard, and with the file system, because the actual mini batches are uploaded to the file system, right? So the persistent storage, right? So file system here means persistent storage. And then there's a client API for labels and fetching previous predictions. So the new box here that's not on the previous slide, because the previous slide was already busy enough. So we also integrate a tensor board, all right? So for retraining, you can, or we automatically sort of provide a URL where you can then fire up, or not you can, or you go to that URL and you can see then TensorBoard, your standard TensorBoard stuff that's coming out of retraining, right? All right, skipping this one, all right, so this slide here just says that, all right, so we're using Istio, so every single part in the Delos system has an has sidecars, all right, so they are quote attached with Istio. So there's the Envoy, actually proxy sidecar, and there's a separate Istio sidecar with every single part. All right, so the key part of this slide here is there's Istio that sort of has sidecars attached. All right, so it's kind of the standard microservice type infrastructure. All right, so some benchmark. All right, so I'm going to go quickly through this. All right, so just one simple benchmark. Sort of, we have a bank marketing campaign data set. We actually artificially create drifts. Right, so this is so we artificially perturb certain mini batches in data. All right, so it's kind of like a supervised drift case. All right, so but that's again because just to benchmark, right? So to evaluate how good is our drift detection module. All right, so and here is, all right, so in terms of accuracy, sort of, we compare this against retraining after every single mini batch, all right? And so the accuracy, sorry, right? So accuracy actually increases by 12.2%. All right, so and here's a chart about drift. All right, so which color now? Orange. No, blue. All right, so blue is the actual drift. All right, so recall that this is kind of, so the data set is not artificial, all right, so but drift is created artificially, right, so which means that we know when we perturb the data. In other words, we know when the drift is really happening, all right, so the artificial drift is really happening, all right. So we compare, so that's the, which one? That's the blue, right, and then we compare against drift detection of our system, and you see that our system detected drift twice where there was no drift, right? So, but it does detect all of the occurrences of drift, right? So it's not missing a single occurrence of drift, right? So on the x-axis, whenever you see D, it means drift, right? But you can also see it from the blue line. All right, so future features I already mentioned, sort of inference as RESTful API, right? So that's work in progress. Fairness and bias, so that's thinking in progress, right? So we have not yet started working on this, right? So in other words, sort of when you do inference, right? So how do you automatically, sort of by means of our system, detect fairness and bias, right? Model serving for unstructured data. Say images and text, all right? So you can currently already do it if you provide embeddings, right? So this actually, unstructured more means actually multimodal data, all right? So that's the pure choice of words actually, right? So if you have images, you can already run them or use our system right out of the box, okay? Because for inference, all right, so you have to provide embeddings, not raw pixels, all right? So you have to provide embeddings, and then Hellinger and everything else sort of makes sense based on embeddings, etc. So you can already use it, all right? But if you want to do inference, say on images and text, right? So one sample corresponds to an image and text. That you cannot yet do it, all right? So that's sort of work in progress. We started, but that we are only at the beginning of the entire implementation, all right? We have not yet also evaluated scalability, right? So we don't know how scalable the system is. Or as I said, yes, you can throw in new nodes, right? So but it doesn't imply that retraining is actually going to scale well, right? So because we know that training doesn't scale, for example, linearly as you add GPU cards. All right, so we plan to do further tests on scalability. All right, so key takeaways, all right, so we have the monitoring component, all right, so Ensemble drift detection, all right, so not just one single prediction, but several predictions, and then we assemble them. Lifelong retraining, right, so which copes with catastrophic forgetting, and we also combine that with multi-arm bandit, so MAB stands for multi-arm bandit. And then sort of it's a framework, it's a generic MLOps framework, right? So not assuming any particular model architecture, right? So generic framework also with algorithmic solutions or enhancements embedded in it, right? So and then sort of there's our flow, right? So which I showed you the diagram, right? So how it goes into how it interacts with Mongo and labels. All right, so those are sort of key takeaways. So we have a current center member that's actually testing DDoS or evaluating DDoS internally on their own use cases. I'm not allowed to share the name of the member company. All right, so we have the first sort of real world sort of use case being under development. All right, so thank you very much. So that's the long website URL. Okay, but if you just type, I don't know why did we put the long one. Just deep learning at Northwestern, not at deeplearning.northwestern.edu. It's going to take you to the center's webpage. All right, and there's no handle for me. All right, so my Twitter handle is @dklabjan. Right, so an email is d-klabjan@northwestern.edu.
Hi, thank you for your talk. You mentioned you simulated data drift by perturbing the data. How did you perturb the data, and how do you measure how much you have to perturb the data?
perturb the data and what perturb as in?
You mentioned on slide, I think, 23, that you simulated data drift by
Yes.
perturbing the data. So how much did you perturb the data? How do you measure that?
That I don't know, to be honest. Yeah, so we perturb it with normal distribution. I know that, all right? So each feature, or actually it's multivariate, right? So it's not each feature. Okay, so I don't know exactly how we create a correlation matrix. Sorry about this. And yeah, that information is not on the webpage. But I can ask. So if you contact me, I'm going to ask the students, and I'm going to give you the answer back.
Thank you. That'd be great.
Thank you.
Thank you for great talk. Could you go back to the slide 10 and
10. Okay. Oh, there are actually slide numbers.
Elaborate on the model to detect the drift.
Okay. Go ahead with the question. Oh, that's. Oh. All right, it's a good exercise for my fingers here. All right. Okay.
Yep, this one. The Ensemble formula to detect drift.
Sure, that's the entire slide. Okay, what's the question? I'm sorry.
How did you come up with this formula?
Oh, the 2 times.
Yeah, 2 times Q1 and Q2.
So that's, as I said, sort of it's sort of, I think it's fairly intuitive that you want to put more weight, more priority, let's say, more priority on classification error or F1 over, for example, over data drift, all right? And so why 2 versus 1? Yeah, so that has been calibrated based on the numerous, based on what, 5 or 6 different data sets. All right, yeah, so the user can actually overwrite 211, right? Because the weights here are 211, right? So the user, through config maps in Kubernetes, can specify different values instead of 211.
So anything in your framework that help to come up with the new weights?
I'm sorry?
Is there any tool in your framework that
no, we don't. Well, so actually sort of, I have not thought about this, okay, but the straightforward way would be through canary deployments, right? So you can, but it's kind of going to be trial and error, right? So you can specify your own weights, and then you trigger canary deployment, so you have your version with new weights running in parallel, and then you can observe in Grafana, for example, drifts, and you can see how it performs based on new weights. Yeah, but that's not a scientific way, right? So that's kind of a brute force, say, manual way to potentially facilitating the choice of 211 weights.
Yeah, that makes sense. Thanks.
Just one question. How does your framework or your pipeline, how does it account for adversarial threats? Because you just talked about like you artificially perturb your system. Well, there could be an attacker that does the same thing, and then the person makes your pipeline actually shift your model because now you're retraining using something or a data set that's been placed in that position just to make your model react in a specific way. How would your model?
So the academic answer is we don't, right? So we don't take into account possible adversarial attacks, right? The practical answer is we have Istio, and you can hook it with DEX, for example, and you can have authentication for every incoming inference batches, right? So now, okay, if you have somebody within your company that is doing adversarial attacks, you have bigger problems than with our system, right? So that's kind of a practical answer, right? So so an outsider cannot inject adversarial samples because of authentication. All right, so that's the practical answer.
Thanks for your presentation. Thanks for your effort to make machine learning retraining and monitoring more simpler. So I'm from domain of design manufacturing, and we have a concept of predictive maintenance. Mm-hmm. So we can predict the remaining useful life of a machine. So for machine learning model monitoring, can we also apply this concept and try to analyze what kind of risk our model is more prone to, or even predict the remaining useful life of the machine learning model?
So to predicting life of your equipment, all right, so yeah, equipment, machines, okay, whatever, right? So you would have to write your own prediction model, right? So, and there are many models out there. This topic has been studied in the machine learning community, right? So, and then, so by using your prediction model, so then if you want to deploy it in practice, you can use our system, right? So in the drift detection model, it should detect drift, right? So, but this is, so this is going to be, all right, so yeah, so this is drift when, so it should detect drift when you're, right, so I guess the relevant aspect here is drift when it comes to data, right? So in a sense, if you have, I don't know, pressure and temperature sensors and whatever else, right? So the drift detection model should detect drift in, with readings from those sensors, right? So if temperature is going to now spike, right? So that's going to be detected by our system, right? So in addition to if your predictive maintenance model is going to make, say, out of whack recommendations, right? So that's going to be detected as well.
Yeah, thank you. I just want to say that for you have a case study where you inject sudden drift and your model can detect it, but in reality there can be some drifts that happens gradually, and can we catch the gradual change of data drift and predict maybe in the future, in a month, we need to retrain the model, something like that?
Yes, yes. So gradual. So here I presented just one study, right? So, but on the drift side, we have done many more studies. Okay, and actually not just one. A few studies have been gradual drift, right? So gradual drift and then sort of quote nothing, and we also studied gradual drift and then gradual decrease in drift, right? Yeah. So we studied all these kind of scenarios.
Yeah. Thank you. Check out your publications.
Sure.
Thanks.
Yeah, it is actually on my website. You have to find, just type my last name and you'll find my
Thank you.
website. Thanks.